Welcome back. This is part 2 in the statics review. In this video we will review how to solve for reactions in statically determinate systems and then look at an example. First, we check that the system is determinate and stable. Second, we draw a free body diagram of the system labeling all forces and unknown reactions. Third, we apply the equations of equilibrium. Note that the moment equation can be applied at any location, but is best applied through the line of action of an unknown, and we will demonstrate that. Fourth, if the solution of the equilibrium equation yields a negative value for an unknown, it indicates the direction of that force is opposite of what you assumed in your diagram. Okay, so here's an example. This is a beam, simply supported beam with an overhang. Notice that it has a pin support at the left end, a roller support in the middle, for a total of 3 unknown reactions. We have 3 equations, so this is statically determinate. Knowing that, I would draw a free body diagram of the system, and I would start out by representing the beam as just a straight line. Then I would add the loads, the distributed load of 3 kilonewtons per meter acting over a distance of 10 meters. So this is 3 kilonewtons per meter. The concentrated force at the end of 15 kilonewtons. Now, it's helpful to label the reactions if they aren't already labeled, so I'll call the pin support at the end here support A. I'll call the roller support support B. And at my pin support, I have the unknown reactions A sub y and A sub x. At the roller support, I have my unknown reaction in the vertical direction only, which I'll call B sub y. Now I can proceed to apply the equilibrium equations. I'll start with an easy one, A sub x. Sum of the forces in x. Okay, this is almost trivial. There are no loads in the x direction, so we see trivially that A sub x must be equal to 0. I typically box my answers. Now we need to solve for A sub y and B sub y. We could do some of the forces in y, but that wouldn't allow us to solve directly for one of the unknowns. So I'd rather apply the moment equation first. And there are a number of choices here, but if I pick, I'm going to pick support A, because the moment due to A sub x and A sub y will cancel out, and I'll be able to solve directly for B sub y. Okay, so let's do that. The sum of the moments at A, and I'm going to consider moments in the counterclockwise direction to be positive. Okay, first let me consider the contribution for our unknown B sub y. We have the force B sub y acting or multiplied by the distance from support A, which is 10 meters. So B sub y, this is our force term. 10 meters is the distance. Next, let's consider the contribution of this distributed load. Note that I can represent the distributed load for this purpose as a resultant force acting right in the middle. And the value of that force would be the distributed load 3 kilonewtons per meters times the distance 10 meters, which is 30 kilonewtons. Okay? The point of action of that force is half the length of the distributed load, or 5 meters. Note that it produces a moment about A that's clockwise or negative according to my sign convention, so I'm going to call it a negative moment. Minus 30 kilonewtons, that's my force, times the distance 5 meters, and that's my distance. Okay, I'm keeping careful track of units. Finally, let's consider the contribution of this concentrated force at the end, also acting clockwise about A, or a negative moment about point A, minus 15 kilonewtons, that's the force, and then the distance over which it acts is the entire length of the beam, or 14 meters. Okay, so that's all the terms that contribute to the moment about A. We set that equation equal to 0 and solve for B sub y by bringing all these terms over to the right-hand side, reversing their signs, 30 times 5 is 150. 15 times 14 is 210. The units are kilonewton meters. We divide by 10 meters. These units cancel and we're left with 36 kilonewtons. This is the value of B sub y. Okay, finally I can use the sum of the forces in the y direction to solve for my remaining unknown, A sub y. I'm going to consider upward forces to be positive. I have the unknown A sub y plus B sub y, which was 36 kilonewtons, minus the force due to the distributed load, a resultant of 30 kilonewtons, and minus the concentrated end force of 15 kilonewtons. All equal to 0. Solving for A sub y, bringing the other terms to the right-hand side, negative 36 plus 30 plus 15 is a resultant of 9 kilonewtons. Okay? Now the last thing I like to do is a logic check. Does my answer make sense? Do I have the right units? Yes, these are both A sub y and B sub y in units of force, kilonewtons. They're both positive, which I expect since these reactions should be balancing the loads which are acting downward. And finally, I observe that B sub y is much greater than A sub y. And this makes sense because I expect the distributed load to be carried equal by supports A and B, but then this concentrated force at the end I expect to be carried more by support B than support A. So this answer makes sense, and I don't know for sure that it's correct, but by doing a logic check you can eliminate many possible errors. Okay, last we look at this problem, which is very similar to the one before. And instead of having a pin support and a roller support, this beam with its loads is being supported by two hanging bars. And the question asks you to evaluate the tension in the hanging bars. Okay, we would do this very similarly as before. We consider tension to be an internal force. So we want to draw a free body diagram that will allow us to evaluate that tension. Generally, I would make a cut in each of the bars, and I want a free body diagram that includes the portion of the beam below that cut, basically the whole beam. Okay? And when I draw my free body diagram and I superimpose, say, my resultant 30 kilonewtons, 15 kilonewtons for the loads, then I would represent these bars. I would replace the bars with the unknown internal tensile forces, T1 and T2. And I'm drawing them in the upward direction, which means that if I get a positive result, the bars are in tension, as I assumed. If I get a negative result, they would be in compression. If we went ahead and solved this, we would get exactly the same thing as we did on the previous problem. T1 equals 9 kilonewtons and T2 equals 36 kilonewtons.